I didn't take the mic out of the thing. I was like, oh, nothing is working. Hi, everybody. Welcome back to Chem 140. This is the last lecture of week 5, which means after today you are halfway done. Hooray! The trade-off on that, though, is that there is an exam coming up. So, exam number 1 is... Oh, there's a cat right there. Where's the cat? Oh my goodness, sorry. Exam number 1 is on Monday. What that means is that it will open on Canvas on Monday at midnight, and then it'll be open for 24 hours. So it closes on Monday at 11:59 p.m. The exam is open for the entire day. You get... I don't know how long you get to do it. It's either 60 minutes or 75 minutes. And you get to do it twice, just like any other assignment that you do online. So you get 2 attempts. Your score doesn't get revealed. I never reveal the answer key to the exam, so you won't see the answer key, but you will get your scores after everyone has taken the exam. I will send out on an announcement this information as well, but in the event that you cannot take the exam on Monday for some important reason, such as like, oh, I work on Monday, and Monday's a really hard day for me to do something, or I have other classes or something, send me an email and let me know. What I can do is I can have you take the exam either on Sunday or Tuesday. So your options are Sunday, Monday, or Tuesday. I would prefer Monday because that's the day I'm going to set it, but I can set it individually for students if you absolutely need to. That said, do not email me on Monday saying, can I take the exam on Tuesday? Because after the deadline passes, if I haven't seen your email, even if you emailed me beforehand, it's too late. Okay? So you have to be preemptive about it. Don't study, and then get to Monday and be like, oh, I haven't studied enough. Can I take it on Tuesday? Because I'll say, no, you have to take it today. Okay? But if you email me tonight and say, I'd really like that extra day to prepare, I'm much more inclined to let you do that because you're preparing in advance. And if you have a reason to do that, like, oh, I have an appointment on Monday or whatever, then of course I will try to accommodate that too. So that's the exam. The exam will cover units 1 through 8. There will also be another quiz for units 7 and 8. The deadline for that will be actually rather short. It will be due Friday, which I realize is tomorrow. That quiz will cover this unit that we're doing today, and then the unit we finished yesterday. Or, I'm sorry, on Tuesday. But the reason that quiz will be due so suddenly is so that when I have the soft deadline would be Friday, the hard deadline would be Saturday. It'll be open on Sunday for you to review and study, and then the exam is on Monday itself. So these questions will show up in similar forms on the exam. So I want you to have that feedback. And I realize that will mean a very quick quiz turnaround, but we'll manage. It's only a 10-point quiz. And then finally, last call for worksheet number 2. Worksheet number 2 is due tonight. You will get an announcement about that after class today. Yeah, so lots of administrivia. So let's get started here. Talk about the periodic table. I found a meme for the periodic table today, which, and by found I mean Steve sent it to me. You might have taken a chemistry class with Steve. Steve teaches 121. He teaches 163. You'll probably see Steve. Can you use engineering notation on the lab instead of exponential notation? I'm okay with that. Yeah, if you want to only have your notations be in powers of 3, I can parse that. What won't parse that is Canvas, so just be mindful of that. Did I get my days wrong? Hold on. I might have gotten my days wrong. I thought it was due today, but it could very well be due tomorrow. Let me check the syllabus. Lab worksheet due. Oh, okay, look at that. Okay, well, hold on. Today is the soft deadline, so we'll just do that. Okay. Okay, yeah, thank you for bringing that to my attention. That was a mistake. This is what happens when you have classes that have things that are due on different days. You mess up everything. So I apologize. Your schedule is offset by my other two classes by one day because we do Tuesday, Wednesday, Thursday, and they're Monday, Tuesday, Wednesday. So I can't keep two schedules in my head. So I apologize. I applied the wrong schedule. Okay, so undo, Control Z, all of that information that I said about lab worksheet number 2. It's due today, but that's a soft deadline. Last call for that will be tomorrow. Good catch. I would not have noticed that until it was too late. All right. So, in Unit 8, we're going to talk about the periodic table. This is a very, very short chapter. Let's see here. Deadline for the next quiz. So the soft deadline for quiz number 4 will be tomorrow. I realize it hasn't been posted yet, but that's because it has Chapter 8 content. And then the hard deadline will be Saturday. So you'll have 2 days to do it, but it's a very simple quiz, relatively speaking. Like, we're in the parts of the quizzes now that don't require a calculator, for the most part. Although calculating like an average atomic mass would need a calculator, but for the most part, you don't need that, since you're just going to be telling me concepts. I mean, presumably you're studying this stuff as you go, so... Alright, so let's talk about the periodic table. Now, in Chapter 1, we gave you a bunch of elements, and it showed that they all explode. So you might remember these videos. I'm just going to click on the sodium here, which you can't see because it's not captured. I don't want to capture it on that box because I've already resized it for p-table. So we'll capture it here. If you did not use all your attempts for a quiz, then those attempts are wasted. Once the deadline closes, I don't let you take it again for any reason. The exception is NQA coupon. So if you miss a quiz for any reason at all, I cannot give you extra attempts. But you do get one free redo for any assignment, and that's the NQA coupon. You can open the quiz. Well, I shouldn't say redo. If you take the assignment and submit it and get a score, that's your score. But if you miss an assignment, you get a free, oops, I missed the assignment, can I take it again? Pass. That's the NQA coupon. That's the only way that that's allowed. If you have 0 attempts. If you have 1 attempt, then you have 1 attempt, and that's all you get. Earlier on the quarter, you saw this reaction with sodium and water, and we showed that with other... I like how everything on my recommended videos now is just like, everything is blowing up, hooray. We saw that elements in that first column, when we put potassium and rubidium and cesium all in there, they all exploded. And the conclusion that we drew was that elements in the same column behave similarly, and that there must be a way that we have rearranged the periodic table so that we represent those properties. And it turns out that that's exactly why the periodic table is arranged into these columns. For instance, all of the elements on the far right of the periodic table, helium, neon, argon, krypton, and xenon, they don't do anything. They're called noble gases. There are elements in the column next to that. Let me get p-table up here real quick. We're actually going to capture it here. There are elements in the column next to that. Let me make this smaller and then bigger. That also have similar properties. So these right here, these elements in this column all react violently with metals. All of the elements in the middle columns here tend to be a little more stable than the elements on the outside. And so we have arranged the periodic table into these sorts of like weird rows. And there's large gaps between them, and there's like this space right here in the middle. But it's arranged in a very particular way. And the methodology for that is behind this guy's logic, Dmitry Mendeleev. Sorry, I'm trying to get my meme ready here. So, Dmitry Mendeleev noticed the following, and that was like, hey, if I notice that there's a certain pattern with my elements, so if this is the periodic line of elements, and I look at elements 10, 18, 36, I can't see the numbers here, there we go, 54, and so all of these guys right here, totally inert. But then if we look at the next ones after that, 11, 19, 37, 55, all of these are violently explosive with water. And if I look at the ones before that, then these are all very reactive with metals, like I said before. And Dmitry Mendeleev said, okay, that cannot be a coincidence. So what I'm going to do is take these elements and just line them up right here so that it goes like this. And then take these and put them over here, under here. And arrange them into a table. And that table will be organized by group, where a group of elements has the same reactivity or very similar reactivity. And so him doing this produced the periodic table. Now, his predictions were so good, based on the logic behind this table, that he predicted elements that did not exist at the time. Like, they existed, but they had not been discovered, I should say. So, one of those elements, it was either gallium or germanium. I want to say it was gallium. So, on his periodic table, there was this blank space between aluminum and indium in the row. Or in the column, I mean. And so he said, okay, the density must be between these two. I bet it reacts with chlorine in the same way that these two do. And when you do that, it will have this sort of density and conductivity and etc. And sure enough, people found something that matched what he claimed, and it was gallium. Replace gallium with germanium if that was the element. But it was one of those two in that area over there. All right, so we have this periodic table here. There are over 110 elements. In fact, we've got all the way up to 118. There are so many elements out there that are available. And I always get this question every quarter, so I'm going to capture this, and we'll see if this works here. Okay, it did work, but it's a little small, so we'll just do it this way. Ah, that's not what I want. Okay. So, Mendeleev invented the periodic table so that people would not have to memorize elements' properties. And then students say to that, do we have to memorize the periodic table? So chemistry teachers make the students memorize the periodic table. Seriously. Don't make Mendeleev angry, chemistry instructors. Don't make your students memorize the periodic table. That is stupid. So if you have an instructor somewhere else who has tried to make you memorize the periodic table, You have my permission to call them a moron, because that's dumb. The periodic table is right there and handy for you to use at any time that you want. Just go to P table. Maya is also complaining. Say hi. Say hi. Say hi, Maya. There you go. Maya also does not want to take the exam. She's going to study right now. She's sleeping on a textbook. You have my permission to tell any instructor who makes you memorize the periodic table that they're stupid. When will be at 500 elements? I actually think the answer to that is never. And there's various reasons for that. So, when we up here, so 118 is down here, where I've put the little yellow splotch. Theoretically, these elements can be calculated, but they've never been observed. And so as elements get closer and closer and closer to where I've put that yellow mark, they tend to last for less time. There is a theoretical island of stability where there will be these like super heavy elements that can be made. But honestly, I feel like if they could have been made, they would have been observed somewhere in the universe. Like in the core of a star or in I don't know. I feel like to make those elements would require so much energy that one of two things is possible. Either you can't do it because it wouldn't be held together, or we don't have a tool that is capable of reaching the energies that we need to bombard large things together and make them stick. I feel like of those two possibilities, the first one's most likely. Like, it's just not something that can hold together. And the reason for that, it has to do with protons and neutrons. Remember that protons repel each other. And that neutrons are sort of like the glue that holds protons together. But eventually you just get too many protons. And that's sort of what's happening here. When you get to 118, it's just like, there are so many protons that no number of neutrons can hold them together. The gravity question you have there's no way I can answer that. Because that would require me to understand what mastering gravity means. Like, right now, we're trying to figure out what causes gravity. Like, what particle is responsible for gravity? Or at least, like, what fundamental thing that we can attribute, like space, for example. And I don't know the answers to those questions because I don't think anybody else does. There are people who are certainly farther along than me, though, but yeah, I don't know. I don't think I can answer the question. Yes, hello? Yes. I'm teaching. Please stop. Sorry, my cat is being needy again. Now, on the periodic table, we're going to categorize it going up and down and also left to right. Going up and down is called a group. So groups are columns. Left to right are called periods. Let me highlight that in a different color. Okay, you need to really stop that. Maya gets the squirt bottle again. Alright, so periods are rows going across the table. Now, we call the rows periods because the patterns that occur in them occur periodically. Every X number of elements, we encounter the one that's completely stable and does nothing. And it's the same number of spaces every time, relatively speaking. There are some hiccups here and there, and we'll show what that means probably a little bit more in 161. All right, so now we know what groups are, and we know what columns, periods are. Groups are the columns, rows are the periods. On this slide here, I have a bunch of names that are useful if you commit them to memory. But again, this is an online class, so you just keep it as a reference. On the top, right here, I have the group number. And these guys too. There are two ways to list group numbers. The first is the AB method, and this is called the old method, I guess, or something like that. And so what you do is you just number it based on the Roman numeral and the letter. So this group right here would be 2A. 2A would be alkali earth metals. 7A would be halogens, for example. Now, a new numbering scheme has been introduced, not super recently, but what it does is it literally numbers them left to right. Like this. Just 1 through 18. It's just numbering them left to right. For that numbering scheme, you just take the number it's in. So halogens would be group 17 instead of 7A. What that means is that on a test or an exam, I'm going to try and indicate both. If I say group 7A, it will also say /17. If I say group 6, it will say /6B, just so I'm clear on which one I'm trying to talk about. On the left side right here, I have the period number. And the period number is just an integer. You just count which row you are in, 1 through 7. Now, what's the deal with these guys down here? They're sort of isolated from the periodic table, and there's a reason for that. It's not really shown on this periodic table, but what these elements do is they sneak in here. So if I write A, I would go from where the first A is up here down to here to continue. And then when I get over here, I then start here again. This is much more clear on p-table. Actually, I probably still have that up, so let me just grab that here. Yeah, here we go. Oh, I gotta capture p-table. There we go. So you can see that on p-table here, there's like this blue region. I'm just going to cover the chat for a second here. There's this blue region here where there's a space, and it says, in this space are where elements 57 through 71 are. So we go down here and start going across, and then we return and keep going. And then we get down here and do this again. The reason that we do this on the periodic table is because we would normally just put this chunk in right here and have everything just get pushed aside. But then your periodic table would be extremely long. Can I make this smaller? I can't actually zoom it out on here. What would end up happening is that the table would just get smaller and smaller and smaller and smaller and smaller, so that we could then stretch it out to make it longer. In fact, if I find a picture of that, let me find the extended periodic table. So this is the reason that that's down there is entirely for space economy. If I could click on a picture of it. Yeah, there we go. This'll work. So there's the extended version of the periodic table, and you can see that this is super awkward to work with. So those bottom two rows should go right there. But because that makes the periodic table just too long and cumbersome, we instead put them down at the bottom and just sort of have this assumption that you're going to slide them in there in terms of, okay, when I get to this point, I'm going to count across and then jump down to the bottom, go across those, and then jump back up. Let's go over the names of the groups here. Group 1A are the alkali earth... sorry, wrong color here. I'm highlighting the wrong color, and now I'm saying the wrong thing. Group 1A are the alkali metals. And group 2A are the alkali earth metals. You may actually see the second group called alkaline earth metals. Totally fine. Either name is fine. I'm going to skip over to the other side here. Where it says inert elements right here, the best name that we have for these is called the noble gases. Noble gases are like all nobility. They sit on their asses and do nothing. Like, they don't react, they don't do anything. They're noble. Group 7A are the halogens. Halogens are really common. For example, a halogen lamp contains chlorine in it. You're exposed to chlorine in the form of chloride every day when you eat table salt. Chloride is abundant, and it's also necessary for life. Fluoride is used in toothpaste. It's very toxic, but it's also very strong at forming ionic compounds with calcium. And then bromine and iodine also serve other purposes too. For example, iodine is important for your thyroid. So halogens are all around us, and we need them. The other important things that I would probably like you to know are just like in the middle here. The transition metals serve as the transition from the left side of the periodic table to the right side. They're sort of just... excuse me. Man, I need to drink more water. They're sort of just shoved into the middle of the table. In the same way that with the extended periodic table, these guys would have gotten shoved in here. Because, as you can see, those should just line right up with each other, and we'd have this nice little block, but we had to put the transition metal somewhere, and this is where we put them. Transition metals are universally metals, that's why they're called that. And they have interesting properties that I spent all of my graduate research time and undergraduate research time studying. So I specifically reacted stuff with platinum, which is right here. I also worked with uranium, which is down here. So I know almost everything there is to know about platinum and uranium. I'm a very specific chemist, I guess. All right. There are other ways that we can use the periodic table to categorize stuff, and that is by this property, metallic character. Now, you might have noticed that on the previous slide that there was a region called non-metals and then other metals, and they were separated by a sort of zigzag. If you are on P table, that zigzag is... Oh, they don't even have that zigzag. Where are my metalloids? There we go. Can I just click on this? Oh, they kind of show it here. Okay. I'm actually surprised that they don't have this on there. Okay. This probably won't... Oh, that was actually perfect. Look at that. Okay. I've clicked on a part of the periodic table, and very faintly you can see here that there's like this gray line that separates these. Many periodic tables have this sort of staircase that I drew in here in red. In fact, here, what we'll do is we'll just get the thick highlighter out here, and we'll just do this. And that's not the pen. There we go. So this staircase is called the metal, non-metal line. And what this means is that everything on one side of the staircase is a metal. Everything on the other side is a non-metal. But anything that touches the staircase, with one exception that we care about, is a metalloid. We'll talk about what metalloids are in a second. I didn't bother highlighting down here because these are radioactive, but the exception is aluminum, which is right here. We'll talk about this in a little bit more detail in just a second, but I just want to indicate where this staircase is for you when we talk about metallic characters. So in general, elements that are on the left side of the periodic table are metallic. And the elements that are non-metals are on the right. So all of your elements that are gaseous at room temperature or form molecules are on the right side of the periodic table. With one exception, of course, because we can't construct the table perfectly. And that's hydrogen up here. Why is hydrogen put over there? People suspect that hydrogen might be a metal if you can pressurize it enough. I just saw this picture right here, and now I'm like, damn it, I should have just gone to this slide here. So here's my only non-metal, but we still put it in the metals category. And then aluminum here is weird. It's considered to be a metal even though it touches the metal-non-metal line. You can see the metal-non-metal line better here. But if you're having trouble seeing it, I will thicken it with the felt tip pen here. You'll notice that the elements down at the bottom there, at the very bottom of the staircase, aren't shaded red as metalloids. That's just because they're radioactive and they don't really last long enough to be analyzed. So on the left side is polonium. Polonium is super radioactive, but it is very metal-like. On the right is astatine. And astatine is not very stable. Sorry, my nose itches. I'm just trying to deal with that. All right. What do we classify a metal as officially? A metal has the following properties, and it must have all of these properties. So the first one is that it conducts electricity and heat effectively. So metals can conduct a current very easily. They have very low resistance. And they also conduct heat very well because all of the atoms in a metal are very close to each other. Heat is just the vibration and molecular motion of atoms. And if all the atoms are right next to each other, they should be able to conduct heat effectively. Metals do that. The next property is that you have to be able to hammer them into sheets or draw them into wires effectively. So metals are malleable or ductile. Malleable means that if you hit it with your hammer, it doesn't deform in a way that it shatters, but it deforms in a way such that its surface area increases. So to make like aluminum sheets, so like when you go to the store to buy aluminum foil, you're buying this really, really, really long sheet of aluminum. You don't find aluminum in sheets in nature. Instead, what you do is you refine it into an ore, which is just a giant sphere, basically, or blob. And then you hit it with a hammer until it is the thickness that you want. Alternatively, once it's thick enough, you could just pull on it. Now, if you want to make a wire out of it, that you just pull it into a one-dimensional entity. So, for example, copper wire, you could just pull on a piece of copper with enough force, slowly enough that it will slowly start to stretch and stretch and stretch and stretch, and it will become a smaller and smaller gauge. And you just stop whenever you get the gauge that you want. The last property of metals is that they're shiny. All metals have high luster, and this is a property of their electron configurations and their conduction bands. Those are words that you don't need to really know. I'm just saying what they are in case like it comes up at trivia night or something. But electrons are very mobile in metals, and what that means for us is that if you shine light on them, that light is more or less reflected right back at you, which means that you see that as shine. You see that as white light. And in some cases, you just see a perfect reflection, such as a silver mirror. Hopefully we all understand why I put Bender here. If you've watched Futurama, you know what Bender says all the time, which proves that he is a metal. Now, a non-metal has none of these quantities. So let's differentiate. A metal has all of the following properties. Non-metal has none of these properties. So, for instance, iodine. If you hit iodine, it shatters into chunks. It does not conduct electricity. It does not conduct heat very well. It would instead evaporate. And it is not shiny. So, what's it good for then if it can't do any of those things? Well, it does other chemistry. Now, on that metal-non-metal line are elements that sort of exhibit some of these properties. So what do I mean by sort of? For instance, silicon. Silicon has good heat conductivity and good electrical conductivity, but it's not excellent. It does not conduct electricity with low resistance. Its resistance is much higher. That's particularly useful for us because when we make logic gates, we want our electrons to go in the direction that we want them to, and not just escape anywhere. If silicon was a great conductor, then by connecting a circuit up to, say, your motherboard in your computer, the whole thing would become electrified. And it'd be impossible to control where the electrons go and get information out of it. Whereas if we used a completely non-conductor, then we couldn't conduct a current through it at all. So silicon's sort of like that middle ground where we have decided, oh, we're going to use this material to build our computers out of because, one, its properties match up with what we want it to do. It can conduct some electricity, but not all. And two, it's abundant. There's lots of silicon out there. In fact, silicon is one of the most common elements. You find it on the beach. It's sand. Sand is silicon dioxide. There's tons of that out there, right? Other metalloids exist for other similar purposes and have varying degrees of conductivity, how easily that they can be cut into wafers or sheets or whatever, and how shiny they are. We already talked about the extended periodic table, so I'm not going to leave that on the table. But what I do want you to do is going over to p-table, I want you to find all of these elements that I have put here, and I want you to tell me the name of the element once you found it, what period it's in, what group it's in. Use either group label. Give me a category that describes it. You can use the categories that we listed, or if you see a different category on p-table, you can list it with that category. And then finally tell me, is it a metal, non-metal, or metalloid? Okay? I'll leave you 5 minutes to play around on the periodic table, and we'll go over the answers together in a second. See you in a bit. All right, let's go over the answers here. So hopefully you had p-table open and were able to identify all of these substances from that. Mostly the point of this exercise is to just be able to look around on the periodic table and then find where stuff is. I'm going to talk about a few like common pairings that we have to be mindful of. Because, for example, like phosphorus is not the same as potassium. They both start with the letter P, but only one of them can be P, and so on. So F is fluorine. Note that the U comes before the O in fluorine, otherwise you get fluorine, which is something you would cook with. I don't know. Just be careful about spelling, because some things, like typing stuff in online, can be sensitive to typing. What is our question asking? So it's in period 2, and it's in group, and you could write either 17 or 7A. Either of those is fine. We're going to give it a halogen. I was going to say category, and I said halogen. We're going to give it a category, and it is a halogen. And then I want to classify it as either a metal, non-metal, or metalloid. It is a non-metal because it does not touch the metal, non-metal line. Next, we've got calcium, which is in period, I got to look it up, 4. Group 2 or 2A. It is an alkaline earth metal. And it literally has metal in its group name, so we're going to call it a metal. What do we got next? We got krypton. And I don't know what period that's in either. That's probably like 4 or 5? 4. There it is. I don't memorize this stuff. I look it up. So you do not need to know what period or group krypton is in. You should know it's probably a noble gas. But that's not something that somebody is going to stop you on the street and it's going to be relevant to, unless you're stopped by Superman, I guess. And that would be kryptonite, which might be a krypton compound. I don't actually know. Au is actually gold. I'm going to put in parentheses its Latin name over here, aurum. This is where Au comes from, is the first 2 letters of gold in Latin. Some elements have Latin names. Gold's in period, I want to say 6. Yeah, period 6. Group. That's 11, yeah, 11 or 1B. It is a transition metal. And it is also a metal. And then finally down here we have thorium, which is named after the Norse deity of thunder, which is cool. Also cool, thorium can be used for power plants, so you could literally be powering stuff with Thor, which I felt is super appropriate. It is in period 7 if you follow the little guide down to the bottom 2 rows. But what the heck do you do here? What's the group number for this? Now, if you said 4 or 5 or something like that, I couldn't fault you for that. But in reality, these don't have group numbers. The elements in the bottom 2 rows, the lanthanides and the actinides, do not get assigned a group number. I'm not going to ask you that on a test. I'm just specifically giving you that question here so that you can see it once in a zero-risk environment that you're not going to be assessed on. But we don't assign group numbers to anything in the lanthanides or the actinides. Now, what name would we assign this? We could assign it all sorts of different names, it turns out. So I'm going to list some common names here. So you could call them inner transition metals. Or you could call it by what row it's in. So the two rows are called oftentimes lanthanoids and actinoids. Because thorium is in the bottom row next to actinium, we would call it an actinoid. Any of those names is fine. To be fair, we don't really work with inner transition metals very much. Inner transition metals for a very long time have been sort of this mysterious, weird thing at the bottom of the periodic table that nobody really knew what they were for. Black sheep. That's actually very appropriate. I actually worked in a lanthanide lab. At UC Irvine, I worked in the Evans lanthanide lab. I don't remember if I told this class about how I worked in the one lab that blew up the year before I got there. I told that story to some other class, but the Evans lab at UC Irvine is specifically lanthanide oriented, but also some actinides, and I got to work with uranium. So I am an expert on uranium chemistry. And just the short version of what sorts of chemistry can uranium do, it's not exciting at all. It does the same chemistry as all the other elements that have a +3 charge or a +4 charge. It's just really big, so you get some unusual things, and I managed to find one of them. And you can actually look up my name and type in uranium in Journal of Chemistry or whatever, and you'll find the article that I wrote. Or at least I was a contributing author to. It's neat, but it's not something that I care about. I just bring it up because it's a thing that exists when we talk about this. It is a metal because it's on the left. Now, even though those two rows are down below, remember that those two rows originate in that space around where column 3 would be. That is far to the left of the metal-non-metal line. So these are all metals. All right, so that's the first hour of the class. When we come back, we're going to talk about some categories. There's only like 4 or 5 more slides to do in the chapter. So let's take our break now. Let me get the timer up here. And I will just hit randomize on the Stardew Valley track list here. And we'll just let it run for 10 minutes. So I will see you in just a bit. Alright, welcome back. Let's finish off the chapter here, which is like... How many more slides is it? Like 4. So, in this second section, what we're going to cover are 2 periodic trends that we can easily map to the periodic table by just picking a position and then moving along the periodic table. And so those properties are going to be metallic character, which we've already sort of talked about, and atomic size by radius. Now, the only reason that I'm really bringing up atomic size by radius is because a lot of what we do in 161 is talk about atomic size. Why are atoms this big? Why is there electron cloud reaching out this far for this atom, but not as far for this atom? I'm going to explain to you the general trends here, and just, you're going to be responsible for telling me how. And then in 161, you're going to explain why using quantum mechanics. You do not need to do that here, okay? But next quarter, when you take 161, and if you do, you'll have me, because I'm teaching all the 161s, we're going to go into nitty-gritty detail about why this happens. But for now, just look at the table and remember that you go this direction and this happens. So that's what we're going to do for this. All right. So the first one, let's talk about metallic character. We already said metals are on the left, and that non-metals are on the right. You can actually visually see that. This is period 3. I have chosen a selection of metals, non-metals, and gases, or metalloids, sorry, from period 3, and you can see them here. So chlorine, obviously not a metal. It's not even a solid, right? Let me get a different color out here. If we move over a little bit to phosphorus, we get to the solid part, but this doesn't look shiny. It looks like if I hit this, it'll break into a bunch of little fragments. Then we get to aluminum, and aluminum is very obviously shiny. If you try and break a can by hitting it, it deforms, it changes its shape, but it's still one contiguous piece. I don't know if you've ever tried to crush an aluminum can by just stomping on it. It's very hard. It resists that effectively because of how it's been engineered, but also because of how metals behave. If you deform it by like puncturing it from the side, then it folds really easily, but it's still one contiguous piece. It's hard to tear it. That requires like a knife or some sort of other instrument to poke a hole in it. And then you get all the way over to sodium, and sodium is so malleable that you can actually cut it with a knife. Like, very, very easily. It's very soft. In fact, you can't make a structural material out of sodium because it's so soft. Not that you would want to, because it would explode when in contact with water. This is why we don't make planes out of sodium metal. The second it rains, it would just explode. So that's metallic character going right to left. So you start on the right side, and you're the least metallic. It's more metallic as you go to the left. So the trend is, as you move right to left, metallic character increases. Things become more metallic. We can do the same thing going up and down the periodic table. This is group 5A, or 15. I'm starting at the top with nitrogen gas. It's a gas, it's not even solid, can't be metal. There's phosphorus again. You could tell that the difference between phosphorus and arsenic is already progressing in a direction of something that is more metal. Because, 1, it gets all silvery, and 2, it looks like the arsenic chunk that we have there is more held together. Like it's less chunky, I guess I would say. Then below that we have antimony, which already looks kind of like a ball of tinfoil. And then finally we have bismuth, which is like, what the hell is that? Bismuth crystallizes in this really weird cubic sort of pattern. But it's completely metallic, it's completely conductive. If you hit it, it won't break. You could maybe chip off chunks of it. But if you like tried to hammer this into a sheet, you absolutely could do that. If you have seen Steven Universe and you know about the crystal gem bismuth, this is what her gem is based off of. That show is surprisingly accurate on its geology, but I think Rebecca Sugar did her due diligence with her work because she put a lot of effort into making sure, like, nothing I want in this show is to be interpreted incorrectly. All right, so that's metallic character. Going to the left means more metallic, and then going down is more metallic. So now I can just point at an element and then point at any other element, and I can ask you, which one is more metallic, aluminum or iron? And you would say, okay, well, I have to move all the way over and down to get from aluminum to iron, so iron must be more metallic. I could do the same thing with, like, chlorine and iodine. Well, iodine's further down, so it's more metallic than chlorine. All right. Let's do the next one. Let's talk about atomic size here. Atoms are really tiny, but they do have different sizes. The size of an atom is based on its electron cloud, which you might initially think has to do with, oh, how many electrons are there? And for part of it, that is true. As you add more electrons to an atom, you have to put them somewhere. You can't just cram them all next to each other because electrons repel. And so the option that becomes available is, oh, I'll just put them further away from the nucleus, so they're further away from other electrons. So as we add more electrons, we get bigger and bigger atoms. We start adding more and more. You can think of them as rings. So if this is my nucleus, here would be my first electrons, and then there would be my second, and then third, and then so on and so forth. Now, not one electron per ring, because I can put multiple electrons in this space. I'm just going to write E here. And as the space gets bigger, you can put more and more and more of them. So as you go down the periodic table, you're adding more layers of electrons, and atoms tend to get bigger. So as you move down, atoms get bigger. Easy enough. Now, as you move left to right on the periodic table, you're also adding electrons. So you might think, oh, atoms should get bigger as I go left to right. And it turns out that that's totally wrong. What? As you go to the right, atoms get smaller. And this is where the weird thing comes in. We will explain this in 161 when we talk about quantum mechanics and effective nuclear charge. But the short version of what's going on here is that every time... Here's my nucleus, we'll say. So let's look at magnesium. Magnesium has 12 protons out here, and there will be 12 electrons floating around my nucleus. Now, if I go from magnesium to aluminum, I add a 13th one, you might think, oh, I'm going to put it here, and it's going to get a little bit bigger because everything else repels from it. But when I move from magnesium to aluminum, I also make this change. Not only do I gain an electron, I also gain a proton. And the effect of these electrons pushing this electron out further, and this extra proton pulling the electron in closer, the winner ends up being the proton, because the proton is pulling it directly to the center, whereas the other electrons are pushing sort of laterally and not necessarily directly away. So as atoms go left to right across the periodic table, they get smaller due to the fact that we're also adding protons to the nucleus. And those protons win the tug of war between the other electrons and the extra protons in the nucleus. That's the short version. All right. Now, the actual reason that we're going to talk about in 161 has to do with what is that force in the nucleus. if electrons are attracted to the nucleus, what charge they feel. It's called effective nuclear charge. We'll talk about it in 161. All you need to know is that if I pick two elements in the same row, and I say which is bigger, the one further to the left is bigger. Atoms get smaller as you go from left to right. Now again, when I say smaller, I am saying smaller in terms of their radius here. Not in terms of their mass, because their mass is increasing. We're adding more matter to them. They're getting more protons. But in terms of their radius, they do get smaller, left to right. All right, those are the two trends. Metallic character and atomic size. So what I want you to do with each of these pairs is I want you to tell me in each pair which element is more metallic and which one is larger. And again, I'm going to make the clarification here by atomic radius. Okay? Go ahead and do these problems. We'll go over the answers together, and then we'll be done. That's all we have today. So see you in a bit. All right, 1 or 2 more minutes, and we'll go over the answers. All right, let me get the periodic table out here. Let's go over the answers here. So I'm going to compare chlorine and sulfur. And you know what? Actually, let me put these on the screen here. That's not the window I'm looking at, is it? There it is. Yeah, there we go. Okay. OBS was showing me the wrong table. What window is this? This is 5. That is way too tiny. We're going to make it a little bigger here. And then I should just be able to scroll this around wherever I want to, right? Oh, I kind of can't. Okay. I can just resize it. That's fine. All right, so I'm going to look at sulfur and chlorine here. I can see that sulfur is further to the left than chlorine. And for metallic character, here's our trend. And then for radius, my trend is... Oh, I should probably squeeze bigger in there. There we go. So I would say that sulfur is more metallic and sulfur is larger. So this is more metallic and larger. What you probably noticed is that these trends tend to do the same thing with the question as asked. The one that's more metallic will also be larger. So now let's do gallium and indium, which you can also see right there. They're in the bottom left corner there. Gallium is on top of indium. Indium is further down, so it's going to be both larger and more metallic. For magnesium and aluminum, magnesium's way over here. So I got to do this. And I can barely get it in there. But that gap, we don't care about that gap there. We just care that magnesium is to the left of aluminum, which means that it is both larger and more metallic. Then we've got calcium and potassium, which are next to each other. Potassium is further to the left. It is larger and more metallic. And then finally, we've got barium and radium, which are down here. Radium is further down than barium is, so radium will be both larger and more metallic. There you go. That's all you have to do. So what you'll see on the quiz and also the exam, you'll see questions that'll be sort these by size, but instead of putting in 2 of them, I might give you 3 or 4. And what you'll end up seeing will be elements that are either in like a line or maybe like a zigzag, but you'll always be able to apply this sort of idea. Which one is furthest up and furthest to the right? That's going to be the smallest. Then which one's furthest down and furthest to the left? That's going to be the biggest. And you could sort the remaining ones by that. Okay. Now, something that we have not discussed is that if you have something like this, so for example, if I compare nitrogen and sulfur, and this is their positions on the periodic table. So one's further to the right, but it's also down. And so you might think, okay, well, this direction implies that it's smaller, but this direction implies that it's bigger. So what's the answer? And the answer is, it's impossible to determine using the trend. And so in that case, you would have to determine it experimentally. So you're not going to see anything where you start going in this direction or this direction, because one trend would tell you one thing and the other trend would tell you the other thing. And that becomes impossible to determine. The 2 trends would cancel out, and so you just don't get an answer. Okay? You're not going to have to do that. Can I go over the... which one again? Chlorine and sulfur. Yeah, sure. Let me find it on the thing here, so... it's way over here. There it is, right there. All right, so there's my sulfur and my chlorine. Remember, more metallic is further to the left, and larger is further to the left. Sulfur is to the left of chlorine, so sulfur is bigger and more metallic. All right, that's chapter 8. Not very many slides on it. That's all we got. Any other questions, let me know. For now, we are finished with the unit, so let me do the little hooray. I forgot to get rid of that. All right, that's all I got. So I do have to call it a day here. I have plans for this evening that I need to get something set up for. But I will be around after that. So if you have any other questions, send me an email. Or drop them in the Discord. And when I have a second, I will go back to that and answer all those questions. I'm going to go open quiz number 4, which is unit 7 and 8. Remember that the deadline for this is going to be very soon. So it'll be due Friday, which is tomorrow. But the hard deadline will be Saturday. And again, the point for that is so that after Saturday, I can unlock all of this stuff. So you have all the answers available. And you can look over those to study so that you have them for the exam, which is on Monday. Please do use the resources available to you for asking me questions. Make sure that you get an email or a message to me in Discord if you have anything that you need me to answer before now in the exam. I won't be able to answer anything on Monday because it will be exam day, and you'll be entirely on your own, unless it's like, hey, my exam doesn't work or something like that. Okay. So yeah, best of luck in your studying. Make sure that you do the quiz between now and then. And I will see you on Tuesday next week after it's all done. Good luck. We're all counting on you.